Hey everybody, so we are going into this next session on the mathematical practices, the 8 mathematical practices that are certainly part of Common Core standards, but will also continue to be part of our standards as we go through the revision process. I don't think there's too much in the mathematical practices that too many folks disagree with. We certainly all interpret them in our own ways. So originally this session was going to be a review of some articles, but in looking at some different articles and some pieces, it just kept coming back to some things that have already been developed. And so I hope you don't mind. I'm going to go ahead and record this session, and this will kind of count as reading the articles. And then after this session, we'll start moving into the content areas. And in those pieces, we'll definitely have lots of access to the good articles from the National Council of Teachers of Mathematics, Teaching Children Mathematics Journal. So we'll jump into that after this session. So hopefully you can find a good, comfortable spot and enjoy, or at least take in this information. This presentation was originally developed by the North Carolina Department of Public Instruction, and so definitely want to give them the primary credit here. I've put a couple twists to it, but 90% of this is from their work back in the fall of 2013, as you can see there on your screen now. And so certainly, again, want to give them credit for this work. This presentation, the original presentation, can be found on the Math Wiki page. And so anytime we want to find those resources, I think we referenced this in our last session, there is the website there on your screen, and these are found under the Professional Development tab. And so if this is useful to you, if you want to download a copy, I'd encourage you to go there and grab it. I'll certainly share a copy of this in our Edmodo group here this summer, but maybe something that you want to grab a hold of as we move forward. So lots of good resources there, both on the 8 mathematical practices as well as what we're all expected to know and be able to do as educators. So what are we going to try to do in this session? Being online, it'll be a little different than if we were face-to-face. There's a lot of time in this where normally we would have done some mathematics or done some turn-in talks. Some of those I'll ask you to reflect on or to share your thoughts on to kind of complete the assignment piece of this session. But basically, we want to just go through and review and make sure that we understand the standards for mathematical practice and where they came from, what do they mean, what do they look like in action. And so we'll definitely do a little bit of math here, but a little bit hard to do virtually in this environment. So that's one of our pieces, is to make sure we're aware of those standards for math practice, and then really just look at how do we implement those standards effectively, and how do we look at them in a way that they are part of something that we do in the classroom each and every day when we're teaching mathematics, so that kids also realize that math is not just the solving of number problems. So that leads us into this question. So I'm going to pause for a minute after we ask here and ask you, what does it mean to be mathematically proficient? I'd like you to think about that as from the educator lens, from thinking about this as a teacher. What does it mean to be mathematically proficient? And then what would you say parents who may not be educators, how would they answer that question? And then maybe is there a lot of overlap? There's some overlap, a little different. So probably going to be one of the follow-up questions you'll see. So I'm just going to be quiet for a minute, give you a chance to think about that. What does it mean to be mathematically proficient? So as you're thinking about that, or as you've thought about that, these might be 2 follow-up questions that would be some good think-through questions. There is certainly a camp of thought that says it's about being able to remember the formulas and to remember 4/3 pi r cubed, and what does that have to do with certain shapes and how you might find their volume, and where does all that fit in, right? Where does length times width that gives me area, where is that being mathematically proficient? Is that part of being mathematically proficient? We certainly have camps of folks who really put great emphasis on formulas and memorizing algorithms that if you're, as you think about an algorithm, we're thinking about, well, when we multiply a 2-digit times a 2-digit number, here's how I write that answer down. Here's how I structure my answer. I make sure I write the numbers in these columns, and as I finish the first row, I make sure I put a 0 in the second row. That whole process piece. Now, so we're going to kind of work through that. Is that what we think about when we think about being mathematically proficient? Is that just part of it? Is that none of it? Like, where does all that fit in? And if it isn't all of it, then what are the other skills? What are the other pieces that might be part of that? And then as another follow-up, we think about the correct answer. This one tends to be touchy too, and is a lot of fun in a group to discuss. There are certainly camps on both sides about the correct answer and how important is the correct answer and when is the correct answer important. We're thinking about when we're teaching children, is it immediately? Is it somewhere within a certain amount of time? Does it depend on the kind of question? There's all those good follow-ups that we really banter about, I think, as educators in terms of the correct answer. And just because I get the correct answer, what does that tell me as the teacher about mastery? Is it possible for a student to give the correct answer and not have mastered the content? Those kind of follow-ups to all that. So as we think about the 8 mathematical practices, I always have to think about the big picture of math. And I have to think, we're really talking about how we approach planning our mathematics, how we approach talking to kids about the math, and then what we're expecting from them and how we're going to give them feedback and how we then expect them to interact with one another. So as we think about all those things, that's really where these 8 mathematical practices come in, right? We're really thinking about what's essential that kids can be able to do in mathematics, more than just the content, not to dismiss the content, of course. The content is very important, and it's important that kids can feel success as well as be successful, but also, can they apply the math? Can they communicate about it? Can they talk with one another in meaningful ways about their math? Are they able to communicate in writing about the math? And then do they realize that all of this math lives somewhere, that there is a concrete representation of that math, that it connects across areas, that algebra and geometry aren't two completely separate areas, that they are in many, many ways very connected. So, and then ultimately, do we expect it to make sense? I think one of those pieces that really made something hit home to me years ago was when somebody asked, do the kids in my classroom, what do they expect the answers to make sense? And of course, initially I thought, absolutely, of course they do. And then the more I thought about it, the more I thought, I wonder if they expect it to make sense or they expect to be correct. And so as you think about your kids, think about the kids who expect the math to make sense, for it to be predictable patterns, and those kids who are just thinking, man, I hope I can get a correct answer here, and maybe you're just following a certain procedure. So going beyond just what is blatantly right in front of us in terms of naked number problems. And when we say naked number problems, we're talking about those kind of problems where it's just, the digits, 12 times 3, and what is that? So when you think about that, this is really our guiding question for today. What are the standards and what do they mean for us? And so Susan O'Connell and John Sangiovanni wrote this book several years ago, certainly just as applicable today as it was when it was initially published. And really, this professional development is built around this text. So many of our schools have this book in their professional library. You can certainly pick it up very inexpensively used, and relatively inexpensively if you want a new copy. And so as you think about these, there are lots of examples of the math practices, and these are the 8 mathematical practices. And you may have a few others that you would add to it in your classroom. Ultimately, we want these to be the the words and the actions that kids are using, not necessarily, well, they are necessarily the ones that we are as well, but having kids put these in their language is important, and we'll look at one example of that here in just a second. But so we're going to work through all 8 of these, making sense of problems and persevering in solving them, reasoning abstractly and quantitatively, constructing viable arguments and critiquing the reasoning of others, being able to model with math, being able to use appropriate tools strategically, being precise, looking for making use of structure, and then finally looking for and expressing regularity and repeated reasoning. So I'd like to pause for a second again and just ask you to think about, of these 8, how do you interpret those 8 in terms of importance? Or is there a particular order that you would go through these? How does that all right now sit with you? And again, you may have great experience with these, and I hope you do. Or you may be coming at these as something relatively new or something you just haven't thought through yet. So let's think about these. What makes sense to you in terms of their structure? Before we get into that a little further, I'll give you another version of the 8 mathematical practices. This is our official version, but it's fun to put them into kid terms, right? And so we've seen plenty of these float around. And so this is one that kind of from a Star Wars type perspective, the mathematical practices of Jedi Masters, right? And if you look at these, they may be a little bit more kid-friendly in terms of their language, and it's always important that kids can interpret or can translate, or that we can help kids translate into their own language into something that's going to make sense for them. So you can see, again, translating those 8 mathematical practices into maybe more kid-friendly language. So this one was certainly just pulled from a very quick, easy Google search, and I'm sure you can find it as well. So as we've implemented new math standards, I remember when we were at the very first year, or the year before we implemented Common Core State Standards for math, and even now as we kind of are on the next generation, or the North Carolina generation, moving into the 18-19 school year of our math standards, the very first thing that we were told from a district perspective was focus on the math practices. And I think we tried to do that, but I think we also probably, the majority of us, also fell into the trap of, okay, that's good, the math practices are important, I totally get that, that's really important, but I also want to know what's the content that my kids are going to need to know. And so I'm not sure how we navigate that better, but as we have implemented new standards, including the standards for mathematical practice, have you run into those struggles? Have you run into what's easier, what's harder? I'll share some of my experiences in talking with teachers and in working with some kids about which ones have been easier and which ones have been more challenging. But think about those things too in your practice. The structure, which I asked you to think about a couple minutes ago in terms of are there more or less important, do some of these come in order? They're certainly numbered, but that doesn't necessarily mean that one is more important than 8 or should come first. I like this layout, and again, NCDPI put this together kind of with the work of the text that was shared there at the beginning, and I like that when you look at this organization, you see that the first and the 6th math practice, so making sense of problems and persevering and attending to precision, those kind of cross the other 6 standards, right? So when I look at the other 6 standards, they all require kids to use standard 1 and 6. They all require kids to persevere, right? If I just look at a problem and say, I don't know how to do that, it doesn't matter if I can use tools strategically. It doesn't matter if I'm looking for structure. I'm not persevering. I'm going to hit a block and I'm going to stop. Right? And then if I'm not attending to precision, then it's really unlikely, right, that I'm going to be able to do something like standard or math practice 8. Right? It's going to be really unlikely that I'm going to look for regularity or look for repeated reasoning. Precision requires me to think about, well, what's correct here and how do I make sense of that? Also, again, if I'm not precise, it's really hard to make a good argument for why I feel that I am correct. So this organization hopefully encapsulates, I guess might be the word, how these 8 mathematical practices fit together. And maybe that's a structure that helps you. Maybe it's not something that's so important for kids, but maybe as educators it helps us think about, oh, that's why those 2 kind of feel, to me, they feel a little different than the other 6. But we are going to work through all 8 of those here, all 8 of these here over the next few minutes. And so let's jump into our first one. And again, the first mathematical practice or standard for mathematical practice is to make sense of problems and to persevere in solving them. I remember one of the very first meetings that I had whenever we were rolling out standards, and I had a high school teacher look at me or actually look at the group at that point and say, well, of course they need to make sense of the problems and persevere in solving them. And no one disagrees with that, right? However, we know that there are plenty of kids who don't, right? There are plenty of kids who don't make sense of their problems and they don't continue to work whenever they run into struggles. So what do we do, right? What do we do in our classrooms? What do we do on a day-to-day basis, on a minute-by-minute basis to help kids realize what it is to be a mathematical thinker? Sometimes we do this really well in science. We talk about what happened first and what's that likely to lead to, and then what would I do next to test something out. But when it comes to math, if we're just thinking about it in terms of numbers, it gets tricky, right? It gets hard when you're looking at 174 times 13 to really think about, well, let me help you persevere and problem solve. It becomes more about, it's easy to fall into the trap of, let me just show you how to do it. Let's just do it this way. So how do we help build mathematical thinking in our classroom? How do we keep kids engaged in solving problems? We certainly all, or at least I can say for myself, fallen into the trap of, at some point you just want to call on a kid who has the correct answer. And so if we're doing everything in large groups, it's likely that we're going to break down to asking one student to just give us an answer or to show us that. Maybe not true for you, but certainly easy trap to fall into. And then how do we really protect the positive attitude and show kids that we're persevering and that other kids and they can persevere to solve problems as well? We talk about these mathematical practices as if they're for kids. They're really for all of us, right? Like, so what do we do when we run into a struggle, when there's something hard and we're not sure what the next step is? And do we shut down? As adults, do we shut down? Sometimes we do, right? So in a math classroom, how do we keep that positive attitude? I remember one time I was working with a group of teachers, and we were asking middle school teachers. So this group happened to be mostly 6th grade teachers, a couple 7th grade teachers, and we were talking about non-negotiables. Like, what do you wish 5th graders came to you with when it comes to math? And so we certainly talked about some content. And at the end of the discussion, it really came down to if kids would just come to us in middle school enjoying math, if they still expected it to be kind of fun, then we could do a whole bunch with them. But we know that when kids learn or they feel like they're learning that I'm not good at math, then we're breaking down that positive attitude, right? And so then we hit middle school and all the developmental stuff goes on in the brain, and that gets really tricky too. So when we're talking about all this, it's the whole child, right? And it's the whole piece, not just being able to solve the math. So how to persevere and problem solve. So that's good in theory, but what does it look like in practice, right? So we've got some tasks here, and we're going to walk through a couple of these. One being choose an operation. Another example being draw a picture, looking at finding a pattern. We might ask kids to make tables, to guess and check, to make an organized list, to use their reasoning, to work backwards. all these are ways, right, of helping kids realize that we don't all just look at a problem and know the answer. I think we know that some kids believe that some kids just know the answer. And there probably are a few kids that, depending on the question or the task, they do just know the answer. But with a good task or a good problem, I need a strategy, right? So teaching kids strategies and having them watch one another work through those strategies is a really powerful way to help build that overarching concept of making sense of problems. So one example of this, right, and we're going to look at this in a couple of different ways here, is to present the same problem, right, but with different questions over time. And so, see, this one's called the holiday tree. So we have this family, and they count the types of ornaments on the town's holiday tree, and they see those different things: stars, gingerbread men, snowflakes, reindeer, candy canes. And so we ask them, right, some questions. We might be in the middle of a fraction unit, or we might just be trying to set kids up to talk about this. So we might ask a question like this, right, like 6 of the reindeer had red noses. What fraction of the reindeer had red noses? And then how would you get that answer? Well, we want to go back to all those strategies, right? If we're teaching strategies, we might focus on drawing a picture, right? We might focus on finding the pattern, on making a table. Depending on what grade level we would be working with might determine what answer we would expect, right? We might expect 6 out of 18. We might expect 1 out of 3, those kind of things. But we need to be able to bring them back to strategy, right? And so strategy is what allows kids to realize that not everybody just comes to an answer. So as we work through this, then we ask those same questions again, or the same scenario again, but with different questions, right? So, what fractions? So we're going to do some of this that's structured and some of it's a little less structured. While it might feel like this question comes immediately after the one we just asked, it might be a day or two later even, right? We want to give kids a chance to play around with content, right? So now we ask, what fraction of the ornaments are snowflakes? So now we've got 12 snowflakes out of 24 ornaments, right? Or sorry, not out of 24. I think I did that first one wrong as I was talking through it too, right? So sorry about that, but we'd go back and obviously have to add all those up to figure out what fraction. Nope, now I talked myself in a circle. My bad. 6 of the reindeer. We were just talking about reindeer. Right now we're talking about overall on the pieces. See, not all math makes sense when we first look at it. What fraction of the ornaments are snowflakes, right? So now we got to figure out how many ornaments are there. What fraction of the ornaments are edible? Well, now there's a question, right? This starts to come in. Just because it says gingerbread men, does that mean they're edible? Sometimes math isn't just as simple as looking at the numbers, right? It requires us to make sense, which is one of our other math standards, right? And then if 6 of the stars are silver, what fractions of the stars were not silver? So now we're bringing in the draw a picture strategy most likely, right? Maybe making a table. And you can feel how persevering in problem solving brings in those other math standards, right? So when we give a decent task or a good task, we're asking kids to use what they know, right? And then we can ask these kind of things, right? The questions, obviously, and I'm sure you do this with your kids, the questions don't have to come from me as the teacher. They don't have to come from a book. That questions should come from our students in the classroom, right? So we give them something like this, or we give them a graph, we give them a picture, and we ask them, like, what are the questions that could go on here, right? And so as you look at this data right now, we've got some kids, right? We've got this Bridget, right, with she has 4 shells, it looks like. And so then what kind of questions could we ask about Bridget? What could we ask about Bridget and Katie together? What kind of questions? And the more kids are writing their own tasks or their own questions, the more opportunities they have to feel they're in charge of the math, right? That the questions really do come from somewhere real. So similarly, right, we could give this kind of the same kind of task here, right? So we got an admission charge, right? Most all of our kids understand admission charges, whether it's the movies, the aquarium, or something like that. And then how could they write questions that go around that? all of this brings in the discussion of traditional problems and rich tasks or rich problems, right? And so we know that the questions that we ask or the tasks that we give our kids either encourage thinking or they discourage thinking, right? So if I ask the whole class or I ask a certain student, what's the answer to number 3 on your worksheet? Well, that kind of narrows things down, right? If I ask something like, what is 5 times 4? And again, thinking this is not just, hey, we're just practicing our multiplication facts, but if I ask that, I either know it or I don't. It's not likely if I'm just calling on somebody for that 5 times 4 that they're going to be able to use a strategy to come up with it, because I'm probably, generally speaking, not giving them the time to think about, well, I know that 5 times 2 is 10 and 2 tens is 20, or use some strategy like that, or to draw it out or to do those pieces. And again, not to get into the discussion about quick recall and multiplication facts, but there are certain questions that are going to make a child feel like they can persevere, or they're going to make a child feel like I'm just not good, right? So our challenge, of course, in teaching is in the flow of teaching, how do I ask those questions that get kids talking to one another, that get them thinking, that get them to persevere? Because if I really believe that kids should make sense of problems and persevere in solving them, then I've got to give them time to do that, right? And I've got to give them the tasks that it will take to do that. So we have some questions here. We have some tasks, I guess. And we could sort some of them into traditional problems. We could sort some of them into rich problems. Oops. And we can think about all the different tasks that we use that we may or may not sort. We're not going to obviously be able to shuffle paper around to one another. So I won't give you all those tasks here right now. But ultimately, right, what we want to do is to think about, how are we equipping our students, right? We want our students to be better able to determine and articulate what a problem is asking. So I've read this problem, now what is it asking? I'm sure we've all taught plenty of kids who they'll read a question, if they don't immediately know what it's asking them, that's it, right? They're done. I don't know, am I supposed to multiply, or they're just going to multiply everything because we're talking about multiplication this week. So are they really articulating what the problem is asking? Can they put it in their own words? Can they draw a sketch of it? We as teachers, right, we're going to ask students, right, to restate problems. We're going to have them turn to their partner, right? And by doing those actions first, and again, we're still going to get into solving the problem, but by doing things like asking kids to restate, by asking kids to do those think, pair, shares, to talk to a partner, we're really helping them realize that they are responsible for, and that they can articulate what a problem is asking, right? If we ask kids to use diagrams and model, or we ask a lot of times, what should we do first, or how do we get started, then kids understand at some point they've got to try to find a starting point, right? If we use familiar problems, right, like didn't we do a problem like this? We see in working with high school kids, it's a really powerful approach, and it works just as well with elementary. It's just easier to see with high school kids, to continually use similar tasks over time. And they begin to realize, like, oh, every time we see a problem like this, we're going to try to do it this way. Right? How can I make it a simpler problem? How can I make this make sense to me? So none of these things are earth-shattering, right? But they are things that on a day-to-day basis we can ask ourselves, are we doing this for our kids to help them achieve making sense and problem solving? So just some personal reflection kind of questions, right? Do we give our kids the time and the space to share what they did, to share their solution and their process? You will see, and I'm sure you have seen, that especially early on, and early on just being early no matter what the age is, the first couple times, maybe the first many times, we ask kids to talk about how they solve something, they often don't have the words, right? They don't know how to share it. And sometimes that reflects not knowing it, and sometimes that just reflects not knowing what to say. So a second kind of reflection piece, right, is do we show kids that we are actually persevering in problem solving, right? Or do we show them that we're just valuing the correct answer? It makes me think back to middle school and high school as a student. All right, what was kind of the underlying message of let me read off the answers to last night's homework and you check your paper and hand it in? You know, it makes me wonder, like, as a student, what kind of message did that send to me, and what kind of message does it send to kids now if we're doing those kind of things? About, is that homework about the correct answer, or is it about how did I get there, or a little of both? And then are we giving kids questions and tasks that actually require them to persevere? And do we give them good questions to guide them as they work through their process? So these two images come from some resources by NCDPI, right? So we've got questions to make the mathematics a little more open-ended, right? Really getting kids to think about their problem-solving techniques, right? Before we ask the question, during the question task, and then after, right? Like some of these are ones that we can certainly just pull out and ask, are we using these, right? So again, these are coming from the text that we shared at the very beginning of this, and then adapted here by NCDPI for us, right? So, what is the question? What are they really asking? Can you put it in your own words, right? What are you going to do with this information? Let's each look at how our partner or somebody sitting around us solved it, and then let's look at how I solved it and decide, did we both get the same answer? If not, is that okay? If not, all those things that follow up with just a good math discussion and a good math task versus the answer's 20. Right? I either got it or I didn't, and we're done and we're moving on. So the first mathematical practice, again, to persevere and to problem solve, and that being one that overshadows or encompasses all the other standards. And that brings us into our second math standard, right? To reason abstractly and quantitatively. So we're thinking again, right? How do I help my kids each day build a stronger understanding about quantity and number, right? That it's not just digits on a page, that those digits represent something, right? They represent something concrete. And then how do we help our kids convert problems and turn those problems into number sentences or abstract representations? And then how do we help kids read those number sentences, whether they have unknowns in them or whether they're just numbers on the page? How do we help kids read those? So what are some different things we might see, right? And we'll look at a few of these here as we go through. So we might look at number webs. We might look at a strategy called headline stories, and some of those are to post it, to book it, to reverse it, to match it, to question it. We're going to look at some examples of those. And then some pinch cards. So we could imagine, if we are all together, right, we could each pick a number and we could think about, like, say the number 17, or better yet, a number like 3.5, right? And so we write that number in the middle, and let's create a web, right? Let's create how many different ways can you represent that? Very similar, asking kids to do it, it might look like this. So you see 1.25 was the number. So how many different ways, or let's come up with so many different ways that we could represent 1.25, because it's not always going to look the same. It's quantity, right? It's not just digits on a page. So it might be an addition sentence. It might be a fraction. It could be a decimal subtraction sentence. It could be a concrete manipulative kind of picture there. It could be a percentage, right? Could be rewritten as a fraction. Again, could be decimals that are being subtracted. Could be a multiplication of a quarter. It could be all those different representations are all 1.25. as we build kids towards this idea that numbers can look different, we're really trying to build that idea of convenient forms of the number. That there are certain times that I want 1.25 to look like 5/4, and there are other times I want it to look like 1 1/4, and there are other times I want it to look like that picture of the square broken into fourths. That each of those is just different forms of the number. So the number web is an easy one. It's one that we can do almost every day. Right? We can come up with numbers that are part of the content that we're trying to teach at a certain time. Another way to help kids reason abstractly and quantitatively, right, is this idea of headline stories, right? Think about a headline in a newspaper, or a headline on a web page. It's really just capturing the essence of that article. And so we can do that for numbers as well. So we'll look at some examples of that. And ultimately, we're helping kids realize that equations come from those kind of things, and we can build those kind of questions, which then turn into equations, which then we solve, right? And they also help us see into the way the kids are thinking and problem solving. So here's one student's an example of one student's thinking. So the question was simply solve the equation and write a word problem that goes with it. So write a story, right? Create the headline story, not some long, not a huge article, but let's just write the headline story for 5 times 1.5 equals some value. And so in this case, the student wrote down, and they've got 1.55, and then they multiplied it out, it looks like, and they said that n equals 7.5. Okay, that would be good, right? That would say, okay, looks good. Looks like the student understands how to do this multiplication, and maybe we all agree, okay, it looks good. And then we ask them, okay, so to write a story problem that goes with it. And he writes, Sylvester has 5 honey badgers. Sebastian had 1.5 honey badgers. They were in a contest to see who had the most honey badgers. If you multiplied them, how many did they have? And then we have questions, right? Say, does the student understand it? Did they seem to understand the process of the multiplication, but do they understand what's going on in that? Without having them write that story, it could just be they don't understand how to write the story. Some people can argue that. We could have a great discussion about that, and it may or may not be true, but ultimately we'd say, would you accept this scenario to give us that solution? And I think we'd probably then agree, well, no, right? So how do we work with that, right? How do we work to get kids from what we see in what this student wrote to what they ultimately need? Well, first off, right, we don't even know to ask them to write it unless we do something like this, right? Unless we have them make their learning visible. Let's compare it to this student, right? So again, we see a very similar algorithm kind of approach on the right. See the same solution. So we'd say, okay, if this was just writing down the digits, yes, they both got it right. But let's compare this student's thinking, or this student's ability to make sense of the problem and to reason abstractly and quantitatively. So this one says, you have 5 pets, a dog, a cat, a hamster, a parrot, and a turtle. So not only do we have 5 pets, we're going to tell you what those 5 pets are. Each pet gets 1.5 cups of food. How many cups of food do you need to feed all the pets? Well, there we go, right? Now we've got the concept, right? So the first student clearly either doesn't know how to write about the concept or wrote, but seems to be showing us they're not really sure about what multiplication means. This student seems to have both the ability to solve it as well as the ability to write about it. So again, these kind of things can be as easy or hard as we want to make them. We can bring in fractions, decimals, percents, variables, all those pieces based upon the content we're either teaching or about to teach, or maybe as a review of something we did back earlier. So we could just say that the headline is 52 divided by 4 is something, and then we'd like you to think about how would you solve that? What would be a story that could go in there? Oops. And so we could certainly come up with lots of solutions. Another strategy are the pinch cards, right? And so these are very simple, just like what you see in front of you here. In a pinch card, every student gets a pinch card like this, which is basically just an index card, and we have the operations on it. And so we're going to ask a question, right? We're going to ask the kids, pinch the operation that you think we're going to need to use to do this. So again, a process to help kids realize that when I'm reading word problems or word puzzles, they should, as I think through them, cue us to think about the operation that is most likely to solve it. We can find a lot of times that more than one operation might be appropriate. So structuring the kind of questions we're going to ask, again, not asking us to go all the way through the solution process, but really focusing on, do I know what to do to solve it? All right, so there are 6 soccer teams in the league and 12 players in each team. Which one would I pinch? Right? You could certainly pinch the plus, you could certainly pinch the multiplication, but if I saw somebody pinch minus or divide, that would tell me something different, right? And so, again, gets all the kids involved, or even if it's a small group, gives everybody a chance to think about it, right? The 4 members of the bowling team scored those 4 scores. What's the team's mean score, the average score? Well, now I might be pinching multiple things, right? I might be pinching addition and division. And so that would show me that a kid really gets that, oh, I've got to do one thing first and then another thing second. So pinch cards, again, something that can be easily in a math tote or on a desk. We certainly just do it this pointing as well. Feel the difference between that and saying, if you see the word more, that means add, right? The keyword approach, we know it's all out there, right? We could pull up website upon website that say, here's your poster to put up in the room that talk about keywords. The problem with keywords, right, are the keywords can be misleading. They can be guiding, but they can also be misleading, and sometimes intentionally so. So when we look at certain problems, some of them don't have any keywords, right? So if I'm telling kids to use a keyword approach, it gets tricky because sometimes there just aren't any, right? And it really sends the wrong message about math, right? If our point in all this is to persevere, to problem solve, to make sense of problems, and then to reason, if I'm teaching keywords, I'm kind of saying, well, you don't have to think about this, just do this. And ultimately that breaks down, right? It's the sense making that we really want to emphasize. The keywords, they may be somewhat of a clue, but really encourage you to think strongly about keyword approaches and how they tend to break down, right? So one example here, we won't belabor this a whole lot because it's, again, a better discussion together in a group, but if we had something like this, Maxine took the 28 stickers that she no longer wanted and gave them to Xandra. Now Maxine has 37 stickers left. How many stickers did Maxine have to begin with? So keyword approach would be to say something like, oh, left, that means remaining, that means subtract. So I'd have 11, and then we'd say, wait a minute, did she have 11 stickers and she gave 28 away? Well, it doesn't make sense, right? If I'm really looking at this in terms of what makes sense, there are so many other strategies like drawing a picture, right? Like all those things we listed in the very first part, right? So the most important thing we want to do with kids, all right, is to help them realize that it should make sense. Doesn't mean it's going to make sense initially, right away when I first read it, but any good poem or any good story a lot of times doesn't make sense right at the beginning. It's when you put all the pieces together and you expect it to make sense that then it does make sense, or then I know that I need to ask for help. When we think about context, right, we're thinking about contextualizing and decontextualizing, and why is that important? So let's look at an example here. Again, all this is about reasoning abstractly and reasoning quantitatively, our second math practice. So we talk about 120 students, 5 chaperones go on a field trip. Each bus holds 35 people. How many buses are we going to need? Right? When I decontextualize it, right, I'm just looking at the data, looking at the action, writing an equation, and then solving it in some abstract way. When I'm thinking in context or contextualizing it, I'm really going back to the problem to see if my solution makes sense or if my approach itself even makes sense, right? So there are times we have to decontextualize, right? Because there's a lot of words, right? I've got to get it down to something more manageable, but I always want to bring it back to the context, right? I want to make sure I'm bringing it back to the idea of quantity. And perhaps you remember this, but I remember my math teachers always talking about label your answers, right? And especially as we were working in science and those places, because those labels force us to think back to what really makes sense. Do centimeters make sense here? This is a measurement type problem. So if we as teachers, right, ask students to identify and describe the data in the problem, and we ask students to build equations, then kids are more likely to make sense of them, right? If we discuss what operations might be necessary, if we discuss modeling, if we discuss diagrams, if we ask kids what makes sense here, how do we build an equation, all those pieces are going to help our kids be able to do what we ultimately want them to do, right? Which is decontextualize the work itself. And so that brings us up to our third standard, which is constructing viable arguments and critiquing the reasoning of others. And when I think about this one, I think about the national board process for teachers, because a lot of it asks you to demonstrate that kids are talking to one another about whether it's math or science or anything else. And that can get really tricky, right? Because kids don't naturally, maybe it's not just kids, humans don't naturally find themselves constructively criticizing one another, right? And coming up with really good arguments that aren't adversarial, right? That are just talking about how I did this and why I think maybe my approach is different or better than yours. So again, how do we get kids ready to justify their answer and to defend their processes? What are we going to do to help them do those things? And then how do we help kids consider and judge the reasonableness of an answer? So what are some strategies? Let's go through the same process, right? So we're going to talk about eliminate it, agree or disagree, and my 2 cents. So in eliminate it, right, as a group, we're going to try to think about the concept that should be eliminated. I'm going to show you an example here in just 1 second. But you've got to be able to give a reason why it should be eliminated. And there can be more than one correct answer, right? So you can create your own, but here's one example, right? So which of those does not belong? Add, subtract, multiply, or join. I might immediately think about subtract, right? And I might say, well, because add and multiply are the same type of process generally, and join means to bring together, and so all three of those have to do something. But another student may come up with another reason to eliminate one or the other one. Similarly, right? Rectangle, circle, cylinder, or triangle. I might see 3 of those as 2-dimensional shapes and 1 is a 3-dimensional shape. Somebody else might think about some other attributes of those shapes and what you can make them from. Or I could give some numbers, right? 21, 17, 83, and 84. My immediate one might be 84 because I think that's even and the other 3 are odd. But I might also look at this in terms of multiples of 3, right? And so then 17 would be out. So looking at how do I get kids to talk about their math in a way that's somewhat engaging, right? And you can certainly take it up to just about any level. So we start looking at unknowns or variables, we've got that too. So that was our first strategy, right? So eliminate it is the first strategy to get kids really thinking about mathematical practice. Number 3, constructing viable arguments and critiquing the thinking of others. So agree or disagree. 75% is more than 2/3 or 2 out of 3. And then why do you agree or disagree? Look at how some students thought about this. So I agree that 75% is greater than 2/3. 75% is the same as 3/4. And because 4 25s make 100, and so 75% is 3 25s. 3/4 is greater than 2/3. Sorry, I had to think about that for a second. So, you know, you could now see into the thought process. Here's another one, right? 5 nickels are worth more than 3 dimes, and why do you agree or disagree? First of all, this is beautiful handwriting, and so whoever wrote this is kudos to them, right? I disagree because a dime is worth 10 cents and there are 3 tens to make 30. Nickels are worth 5 cents and there are 5 nickels, and 5 nickels is 25, and 25 is less than 30. Okay, again, able to see the thinking, and you could see how a variety of kids could think about that differently. So this idea of agree or disagree, right? I can put myself as the teacher in kind of the compromise position of you can disagree with me, which is kind of fun for kids, of course, right? So agree or disagree. Jim has 12 pencils, Annie has 8. Jim has more than Annie. And again, just different ways to think about agree or disagree in context that we might use with the variety of age levels of kids, and maybe make some of the problems off of a worksheet or problems that kids might encounter a little bit more interesting, right? So my 2 cents. So you think about what does 2 cents, what does that mean when we say about, let me give you my 2 cents? So we're giving kids arguments, right, that have flawed logic or incomplete logic. And so then we're asking them to say, so here's how I solved it, or here's how this student solved it. Do you agree or disagree with this? And I like this kid's, right? This is way wrong. It just goes left to right. For example, you can't do 3x squared minus 3. They aren't like terms. So again, you're getting into that who gets it, right, and who doesn't. By presenting kids with incorrect or alternate ways to solve a problem, you can really see what they're thinking. And then finally, it's really important, or it's always important as we're working with kids and or adults, right, to talk about the difference between an assertion and an argument, right? An assertion is what it says here on the page, right? It's right because I know it, right? I followed the steps. It is what it is. Versus an argument, right, that is backed up with facts. So viable arguments are not necessarily assertions, right? You have to have facts or data or reasons to back up an argument, where with an assertion, I could be totally wrong, but I can assert that this is what I think. And so again, how are we as teachers going to build these ideas? We're going to ask good questions. We're going to set high expectations for justifications. We're not going to let so again, we're not trying to beat kids up. We want them to realize that they have this knowledge. They're making decisions, but they need to make them grounded in something, right? We want kids to use the appropriate level of math vocabulary. And then ultimately that helps kids realize they have to use their assumptions and definitions, all those things, to construct a good argument. And that brings us up to standard 4, right, which is to model with mathematics. So what does it mean to model with mathematics? Well, is this just a teacher task, right? Is modeling with the math, is that just something that I have to do as a teacher? Or is that something that I'm going to expect my students to do as well? And then what does that look like for students? And ultimately, how does that affect me as a teacher? So 4 strategies we might try. Model it, part whole mats, bar diagrams, and then bar diagrams for solving equations. It's like you to think about, right? How would you model 125 plus 57? What would you do to model that? How about this one? What about 1 minus 1/3? How would you model that out? And finally, something like 3 4/10 and 5 7/100. How would you model that out yourself? How would you want your kids to think about that? So building those models, constructing them, showing kids that place value in these cases matters. There's ways we can represent. There's multiple ways we can represent that. Thinking about part whole mats, kind of a version of a Singapore math strategy or a bar diagram strategy, right? 2 yellow lollipops and 3 red lollipops, right? We can draw that out, right? There's our 2 yellows and our 3 reds. And then what does that give us, right? Where is that going to come out? There are 6 children. 3 of them happen to be boys. How many of them are girls? Well, now I've got the total, right? So I've got 6 children. 3 of them are boys. Well, now I've got to figure out that part, right? So when I've got when I've got a problem where I've got parts and wholes, this works out pretty well, right? 5 cupcakes. Jan ate some. There are 2 left. So I start with those 5, right? There were 2 left. Now I'm trying to figure out where did I start, right? And again, these are all structures that we see in not just test items, but in real world scenarios, right? 3 boxes, 6 toys. So as we move that into a more advanced way, we look at bar diagrams. It's not just part, whole all the time, right? In this case, there are 3 boxes, 6 toys in each box. How many toys are there? Well, I'm going to have to think about that in terms of all 3 of those parts. Versus I could flip that around, right? 18 toys are packed equally, so I've got 18. So I've got to break that into 3 equal boxes. 18 toys are packed 6 to a box. How many boxes? So now I've got that 18, but I don't know how many parts I'm breaking it into. So now I've got to figure out how many of those elements are going to come in there. So I end up with a very similar looking picture, but a very different problem, right? And so what are we doing to encourage students' abilities? We ultimately want kids to be able to make models to simplify a situation. We want kids to be able to figure out what's the best model for them. It's not what's the best model for me as the teacher necessarily, it's what's going to be the best for them. And some questions that might guide us in that process. So at this point, I'm going to stop this recording, and then we're going to come back and do 5, 6, 7, and 8, just so these videos aren't incredibly long. So I'm going to stop this one, and I will rejoin you with Exploring Standard 5 when you come back.